Guys, so today we're going to do a few examples of trigonometric substitution. I'm going to try to make several videos on this topic because I know it can get a little confusing. So we're going to do, the more we practice, the better. So start with some easy ones. So let's say we have x squared minus 9 dx. Okay, so as we did before, remember how you're going to pick your trigonometric substitution. You're going to look at the type of expression you have. Here you have a subtraction. So the big guy, or the guy on the left of the subtraction, the one you're subtracting for, better be the hypotenuse. So that's going to be x. Remember, we're doing square roots here. Put your angle here, and whenever you have that, you're going to take your square root is the other side, square root of 9. So that's going to be 3. Where do you put it? You put it here or you put it here? Well, remember, you're going to have x divided by something, or x divided by something here, and that is going to be hypotenuse over adjacent or hypotenuse over opposite. What that means is you're going to end up with a secant or cosecant. Those are the ones. So you put it here, so you get a opposite over adjacent, which is going to be your secant. And now in here, you get the square root of the square of the uh, difference of the two of them. How do you get that? In case you're wondering, well, if you were just to call this side b, then you would have that x squared is equal to 3 squared plus b squared. That's the Pythagorean theorem. And then to solve for b, you would subtract this 3 squared on both sides. That is also known as 9. So I put x squared minus 9 is going to be equal to b squared. And then you're going to take the square root, remembering that this is the side of a triangle, so it's going to be positive. So b is going to end up being the square root of x squared minus 9. All right, so with that, then we obtain this over here. All right, so I want to remove that in case I need more space, but that's just for you to know how I did it. All right, so with that, then my substitutions, I want to write them here. So x over 3, as I said earlier, is the secant because adjacent over hypotenuse is the cosine. But now you're doing the reciprocal. You're flipping the fraction, if you will. So you're doing hypotenuse over adjacent. That is going to be secant because it's the reciprocal of the cosine. So we get x equals 3 secant. And then we take our derivative. Dx is going to be equal to 3 secant times tangent of the angle of theta, d theta. And then you look at the tangent, which is going to be square root of x squared minus 9. Why am I trying to solve for that? Because, well, that's what I have right here. So it behooves me to solve for that one. So I do this over 3 is the tangent. Why do I not do, say, for example, x squared minus 9 over x? Well, because I'm introducing an x that is nowhere here. So I would then have to fix it. I could do this divided by this would be the sine. Then I would end up with other terms, which would end up being a cosine, what I'm introducing, and would give me a tangent. Anyways, much easier to go this way. So in any case, I get that the x squared minus 9 is going to be equal to 3 tangent. So I can now substitute that in. So I want to grab this right here. That's going to substitute this. And my dx is going to substitute this. And so what do I get then? I get that this is equal to, I get 3 tangent times 3 times secant times tangent. So let's do the numbers first. 3 times 3 is 9, so let's put it out here as 9. Secant is only one of them. And then I get tangent and tangent, tangent squared. And then the theta. I wrote dx. The d theta. All right, so now here we're gonna try to figure out how to solve this one. So what I'm gonna do is I'm going to convert this tangent as secant squared minus 1, and you'll see why in 1 second. Sorry about that. little break there. And so why would I do that? Well, for two reasons. Firstly, I'm going to have a 9 secant cubed. I could write it even secant squared if I wanted to. That's probably the easiest way to go about it. Anyways, I already wrote secant cubed. It's okay. Minus secant of theta d theta. But now, let me copy this 9 integral of the secant cube. Now, you have a cube of a secant. You know that's going to be integration by parts. We could have done integration by parts here as well, but it's not as pretty. At least I don't think it is. But then you get the secant, which is already the natural log, the integral of the secant, natural log of the secant plus tangent. And it would be a good idea to separate this out. All right, so now what I'm going to do, I'm going to do an integration by parts there. So let's go ahead and continue here, where I'm going to put u as secant. Du will be secant times tangent. Now, if I picked secant, what am I left in this integral? I'm left with a secant squared, so that's going to be my dv. dv will be secant squared, barely going to fit it, d theta. And then v would be the integral of this, which is just the tangent. The derivative of the tangent is the secant squared. Ooh, small there, but we're able to fit it. So now this integral, which by the way, I should call this right here a 9i. So this integral here is going to be I. I'm going to use that again. So it's going to be one of those tricks where you integrate and then subtract and then get your solution. So that's kind of where I'm going for. So the integral here is going to be 9 times uv, so secant times tangent. By the way, the 9 also multiplies this one. I dropped it for some reason. But it doesn't matter. Well, it does matter, but what's going to happen is I'm going to factor that natural log. That's what I was going to do. So I'm going to factor that natural log, and you'll see why in a second. You don't have to do it in the first step as I did, but it's going to be convenient to organize things this way. So that's going to be uv. I move this guy here, and then minus vdu. So I'm still going to have the minus 9 vdu. But notice what vdu will be. Vdu is going to be the integral of secant times tangent d theta. That's going to be your du, but you have another tangent. V is tangent, du has another tangent, so tangent square. So guess what? That's just going to be my 9i. So I get 9i is equal to that 9. 9 is a common factor to everything, but oh well, that's what we're going to do. Secant tangent minus the natural log of secant plus tangent minus 9i. So what I can do then, I can add 9i on both sides and get that 18i is going to be 9 times this whole thing again. Let's see if I can copy paste it in a let's paste it here. Oh, I got the bracket. Oh well, I copied more than I wanted. So I can divide on both sides by 18. So if I divide by 18, this is going to be 1/2. I know that's not the best way to do it, eliminating things. However, the reason why I'm doing that is because I want to be able to, I still have to scroll. I wanted to be able to see this part. That's going to be useful for me to take back all my substitutions. In any case, I have that the quantity I'm looking for is 9i, okay? And I have here the value for I. So if I write 9i, which is what I want, so I probably shouldn't have divided by 18. I should have just divided by 2, I suppose. Oh well. It's going to be 9/2 of the secant of theta. And this is why I wanted to have things somewhat visible there, because the secant of theta is x over 3. Let's zoom out just a bit so we can see it. And then the tangent. The tangent, we said, is x squared minus 9 over 3. Minus the natural log of the secant, which is going to be, again, x over 3, plus the tangent, which is going to be square root of x squared minus 9 over 3. And now I'm going to do a plus c at the end. So this could be reorganized as the integral I wanted to find is 1/2 of x times square root of x squared minus 9. All I'm doing is 9 is 3 times 3. There's a 9 in the numerator and 9 in the denominator. And then I'm going to go ahead and move my 9/2 to this one, distribute it to this one, because this one still needs a 9/2. And then the natural log of, now I can do a common factor x over 3, and then that sorry, 1/3, sorry. So I can do a common factor 1/3, and that then I can write the natural log of this term plus natural log of 1/3 by separating it, but I can then absorb that natural log of 1/3 into the c. So what that allows me to do is just get rid of that denominator by incorporating into the c. If you didn't like that, you don't have to do that. So that's just to make it look a little bit pretty. And that gives us our answer right there. All right, so let's do another one. So in this case, we have the same situation. So I guess this video, I'm going to call it examples of trigonometric substitution that involve the secant or something like that, because apparently that's what I like for this one. So that's actually good. I can make a video for each type of substitution. I suppose that's not a bad idea. Well, things just happen. So again, my triangle, I look at this part here, and that tells me that if there's a subtraction, one of them has to be the hypotenuse, and the one that has to be the hypotenuse is the first guy, because that's what I call the big guy. So if that's the big guy, then I have a square root of that x squared is x, assuming a positive x. And then here I can choose to put it here or here. And as we talked in the previous example, we put it down here because otherwise we get a cosecant. And why is it that we don't like a cosecant? The only reason is because the derivative of the cosecant is negative cosecant cotangent. So you're going to be throwing an extra negative in there that, not great to deal with. Not that difficult anyways, but anyways, traditionally we just do secant, so we'll keep with the tradition. It's obvious I have h because I would do whatever I wanted when I was a student, but oh well, those days apparently are gone. So let's go ahead on our substitution. So x over 2 is going to be our secant. Again, 2 over x is the cosine because it will be adjacent over hypotenuse. So the reciprocal of 2 over x is x over 2, and the reciprocal of cosine is secant. All right, so that gives us x equals 2 secant. So that x is going to be good because we need an x squared there, so we're going to throw it in there. And then we will need also that square root. So I'm going to do square root of x squared minus 4 over 2. That is opposite over adjacent. That's going to be your tangent. So the square root by itself is just going to be 2 tangent. All right, so we put everything together. So this guy will go here. And I suppose I'll need another color because I need a dx. Let's compute the dx from here. Dx is going to be 2 secant tangent. Okay, beautiful. So now maybe I will change my color here, not for the pen, for the highlighter. Let's do a green for the dx. That doesn't even look like, oh, I didn't change it. Let's do this one. And so the green will be our dx. So let's put it all in. And so I need the green, which is going to be, I need the green. Yes, I need money. No, I'm kidding. What's wrong with me today? So that, now we're going to have secant times tangent, and then we're going to put in x. I can put that in. It's going to be 2 secant, the whole thing squared. So the square of 2 secant is going to be 4 secant squared. And now that is going to be a 2 tangent, and everything d theta. Ah, very nice problem, because this one cancels with this one, and this one cancels a square, and a 2 cancels a 2. Anything else? I think that's that. So we get a 1/4 of the integral of d theta over secant. And this one is even better than before, because much better than before, because this one is just going to be the cosine. The reciprocal of the secant is the cosine, so you just throw the cosine in there, and this is just going to be 1/4 of the sine of the angle plus c. Now for the sine, you just look for what the sine would be. The sine is opposite over hypotenuse, so you write that. Opposite is the square root of x squared minus 4 over hypotenuse, which is x, plus e. So maybe we put the 4 down here and make it look all pretty. And that gives us our derivative, antiderivative. Goodness. All right, let's do one more of these and then we'll wrap up this video. So we have, let's say, dx. Let's throw an x here. Oh, that's too easy because we can. Okay, let me show you this. Let's say I give you that. Well, this one, notice, don't forget your other techniques of integration, because this one would just be a u equals x squared minus 9, because du would be 2x dx, and then you notice that you have your x dx is there, and then this you didn't have to do anything really, because that's going to be your square root of u, and then you're going to have a 1/2 of the du. This is a straight up u substitution. So when I wrote that problem, I was like, oh, wait a second, that's not good, because then you don't do trigonometric substitution. So be mindful that you don't always have to do trigonometric substitution when you have these squares or difference of squares or sums of squares. There will be times when you will actually will not need that. All right, so let's take a look at this one quickly. I thought about another problem, so I may end up doing a long. I'm just gonna set this one up, and then I'm gonna show you another type of problem. Again, so I have the difference of squares. The big guy will be the hypotenuse. So now you're bored of these ones because you know there's gonna be a secant. So I'm gonna put this as 3 square root of that, and here it gives me the square root of x squared minus 9. So I get that the secant, and we're just gonna write x is gonna be 3 secant. You know now the drill, because x over 3 is the secant, so I multiply times 3 on both sides. The square root of x squared minus 9 is going to be 3 times the tangent. My dx is going to be, well, would be nice to put the angle, right? That actually happens a lot when you are, because the way we say it, we say, oh, 3 times the tangent, and then we start dropping the angle when we talk, and then when you write it, you drop it as well. Please do not drop your angle, because just the tangent by itself means nothing. It's just a function that has not been evaluated, so it's not what we want to be doing. So be careful with that. That happens a lot. So plugging everything in here, you would have that x is going to be 3 secant. The dx is going to be 3 secant tangent. You see, I just said a secant of theta, tangent of theta, d theta. And then here you have a 3 tangent here. and you see you cancel 3, cancel tangent, and you end up with a very similar integral than we had before, the secant cubed. So we're going to have 9, and with a 9 as well, secant cubed. And then from there, you'd have to do your integration by parts and play the trick, play the game with the I, and so 9i equals, and then minus 9i. Do the whole drill. It's gonna be something similar to what we got for the first one, except it's not gonna be the same, because remember what we had before was we had that that secant tangent square, so we had to use an identity to convert it into this, but it should be very reminiscent. Obviously the integral is not going to be the same, because before we didn't have an x squared, and the x squared minus 9 square root was not in the denominator, was in the numerator. Nonetheless, I want to show you one more type of problem, so let's go ahead and move on, and let's cook up another one. So this is going to be a little bit I don't want to do it too easy. Let's see what this one comes out to be. So let's just do dx, and let's do the square root of let's do x squared minus 6x, something like that. All right, so when you have something like this, what do you think of? Well, what you probably will think about is factoring an x and seeing what you can do with that, and it's not going to take you very far. But what you should be thinking of, which we've done before, so maybe it does ring a bell, it is completing the square. So I'm going to be adding something to this, and then I'm going to subtract that same quantity over here. So what am I going to be adding? Well, remember, you're going to divide this by 2, because this is a coefficient 1. So divide by 2, negative 3, then you square it. Negative 3 squared is 9. And that's going to be the quantity that will complete your square. All right, so what does that do? Well, what that does is that we have dx, and then the square root of, and then I have x minus 3 squared, when I factor it, minus 9. And that then turns into a triangle. Again, they have a difference of squares. So you do your hypotenuse is going to be now x minus 3, and your adjacent to the angle theta is going to be 3. And then here you get the square root of this, which is the same thing as, if you want to write a little bit less, when you FOIL it out, it's going to be x squared minus 6x. All right, perfect. So now we can do x minus 3 over 3 is secant. I'll just write equals 3 secant. I think we've done enough of this. 3 secant. And now we're going to have the square root. X squared minus 6x over 3 would be the tangent. So let's write it as 3 tangent. And now this is the nice thing, that this came out to be linear. So then dx, because the derivative of negative 3 is 0. So dx is the same as before. Secant tangent d theta. And that we can then plug in. So we have 3 secant tangent d theta. That's the dx. Maybe we should call, whoa, not that. Don't cross it out. That's my dx. And then I'm going to write the square root in the denominator, which is that. That becomes 3 tangent. And you see how now I'm going to cross it out. The tangent cancel the tangent, the 3 cancel the 3. As this one turned out to be a very nice problem. We cooked it up in the fly. Well, on the fly. Oh well, it just worked out nicely. But it makes sense because it's similar to... Is it? No, let's leave it at that. It worked out. So this is going to be natural log of the secant plus tangent. I was going to say something was wrong. Would be the first time, right? Right. All right, so secant, now I can solve for my secant, which is going to be x minus 3 over 3. solving from here, plus tangent, which is going to be solving from the next one, square root of x square minus 6x all over 3 plus c. And then this one, you get to simplify a little bit because there's a 1/3 common factor. So you can just say natural log of, if you want. This was already pretty nice. But the 1/3 common factor can go away. X minus 3 plus the root of x squared minus 6x plus c. And that's that. That's what we get. All right, we'll wrap up the video right here. It's already quite long. So thank you for watching, and I'll see you in the next.